Hello student, welcome in today's session. I am Professor Fayaz Kavadi from Department of Mechanical Engineering. This is our module 10, stress, shear strain, energy and power. In this module we are going to study the different empirical formulas for stress on shear plane, shear strain, energy and power. From unit number 1, theory of metal cutting, from manufacturing process to subject. So what is shear strain? Shear stresses develop on the shear plane. Let A suffix S is shear plane area in mm square. Area at the shear plane, area of material or area of chip on the shear plane in mm square. A0 is chip flow area in mm square, or you can say it is the area of chip or area of material before cutting, uncut chip thickness, which is denoted by B into T. In this figure you can see this is the shear plane on which force Fs is acting, shear plane on which Fs force is acting. For understanding the shear stresses which are developed on that plane, I will do one construction. I will draw the straight vertical line which is perpendicular to force Fc and meet at point on the shear plane. Shear plane is denoted by phi here. So you can see here the triangle BAD. Due to this vertical line which I draw through point G here, this triangle is formed here. That triangle will be BAD, in which AD is perpendicular to shear force FC, and the angle ABD is a shear plane angle denoted by phi. On that triangle I am going to concentrate to you. Okay, in that we have to find the area of uncut chip thickness, which is denoted by here A0. A0 considering the width of the chip. Okay, and AS is the area of material on shear plane, that is AB, on AB, that is AS. Okay, that we have to find out to find the stresses, because stress is the load upon area. So we have to find out area A0 and area AS. So in this figure you can see that triangle ABD, the triangle, and in that you can see the isometric view of the triangle, in which you can see the width of chip also, width of uncut chip also, and width of chip of material on shear plane, which is same. B1 is denoted here, uncut chip material width, and width of the chip on the shear plane, that is B1. Okay, so considering the sine phi is equal to A0 divided by AS. Why I consider that A0 divided by AS? Because sine phi is equal to opposite sine AD divided by hypotenuse AB, in which B is common factor, width of chip before cutting and width of chip on the shear plane will be remain same. So B1 and B1 will get cancelled here. So it will become AD divided by AB. Okay, if I consider that width, this will become A0, which is dotted hatch portion, and AS is the section or area which is shown by horizontal hatching line, that is AS. So this will become sine phi is equal to A0 considering the width divided by AS. So what is the value of AS? AS will become here A0 divided by sine phi, and A0 is nothing but B into T. Uncut chip thickness, that is T. Here it is denoted by T0. Why? Because it is showing the area of A0. That's why it is T0. But for expression, I'm taking here only B width, because that width will be same on A0 area and AS area. So I'm considering only B into thickness, that is T0 here denoted here T0. I'm considering T only. A0 is equal to B into T divided by sine phi. So average shear stress, we know, we learn what is the formula for stress. It is the load upon area or force upon area. So which force we have to consider? So and force is equal to Fs, force along shear plane, Fs divided by area of shear plane. Area of shear plane, that is average shear stress, which is denoted by tau. Greek letter tau. So tau is equal to Fs upon As. In that Fs, we learn that what is Fs formula for Fs is equal to Fc into cos phi minus Ft into sin phi. Fs is equal to Fc cos phi minus Ft sin phi. I will share the link of previous video. In that we derive these formulas. Fs equal to Fc cos phi minus Ft sin phi. Putting the value as Fs here divided by As. What is Af? As d into t divided by sin phi. So moving that sin pi to numerator. So this will formula for tau, average shear stress, will become here Fc cos phi minus Ft sin phi. This sin phi will move to numerator. So this will become into sin phi divided by d into t. Remember this formula for solving the numericals while to find out the average shear stress. Now, next point is average normal stress, which is average normal stress. So you have to consider the force along normal plane and area along normal plane. Okay, so this will become here stress, average normal stress is equal to Fh, force along normal plane, divided by area of shear plane. That will remain same in both the formulas. So what is the value of Fn? Fn is equal to Fc sin phi plus Ft cos phi. Fc sin phi plus Ft cos phi divided by B into T divided by sin phi. That way area will remain constant. This will remain same in both the formulas. So average normal stress is equal to Fc sin phi plus Ft cos phi into sin phi divided by B into T. That is the formula for average normal stress. Remember this formula and write down in your notebook. Next a bit is a shear strain denoted by epsilon. Shear strain denoted by epsilon. So in this figure you can see the tool is removing the material, and due to the deformation the chip is removing. Chip 1, 2, 3, 4, 5. These are the layers of material removed from the workpiece, and chip number 6, 7, 8, 9. This is the part of uncut material of workpiece. So there are number of layers of the chip 1, 2, 3, 4, 5. Here you can see with a rake angle. So for analysis purpose, I will consider only the chip layer number 5. Layer number 5 here for derivation purpose. Okay, and in that I will consider that area only. Sliding area ABC for shear strain, ABC, and in that I will draw, in that triangle ABC I will draw the perpendicular line BD on line AC. I will draw the perpendicular line through point B, which will meet at point D on line AC. So angle ADB is 90 degree and angle BDC is again 90 degree, and this will be the rake angle of tool alpha, and this is shear angle. In this figure you can see this is a phi, which is shear plane angle. So this angle will making angle with horizontal line by shear plane. This is shear plane. Okay, AC is a shear plane. So shear plane is making angle with the direction of cutting, that is shear plane angle phi. So we have to find out this angle. For finding the shear strain, we have to find this angle. So what will be this angle? This will be phi, this will be 90 degree, and this remaining angle ABD, this angle will become 90 minus phi. This angle will be 90 minus phi. This angle will be alpha, and we have to find out this angle included between these two angles. So this will, and this total angle AB and this vertical line making angle rake angle is total 90 degree. So this angle will be 90 minus phi. This angle will be 90 minus phi plus this unknown angle that we have to find out, plus alpha is equal to 90 degree. So unknown angle will be this 90 will get cancelled. Okay, and unknown angle will be phi. If you move it this phi and alpha to the right side, this will become phi minus alpha. So this is written here, phi minus alpha. So understood? What is this angle? Phi minus alpha. So shear strain is the displacement of layer CA. Shear strain change in length to the original length. So this is the basic formula which you learn in strength of material subject. Shear strain is displacement of layer CA divided by thickness of layer DB. Thickness of layer DB. So shear strain is equal to CD plus DA, which is AC divided by thickness of layer DB, that is DB. So here I split that numerator here, CD divided by DB plus DA divided by DB. So epsilon shear strain is equal to CD by DB plus DA by DB. So epsilon will become here. What is CD by DB? This is phi. Okay, tan phi is equal to dB by dA, but the reciprocal of that will become dB by dA. This will become cot phi. dB by dA, this will become cot phi plus what is CD by dB? CD by dB, that angle we have already found out, phi minus alpha. So tan of phi minus alpha is equal to CD by dB. This will become CD by dB. So shear strain, the formula for shear strain will become here cot phi plus tan of phi minus alpha. So also remember this formula for solving the numerical. So this is regarding shear stress and shear strain. Now come to the next and last point of this bit is specific energy and power. If F is the feed in mm, measured in feed in mm, and D is the depth of cut in mm, then area of cross section of material to be removed is F into D. Why? Because in orthogonal cutting, feed is considered as thickness of chip, and that thickness is nothing but T, and this is uncut chip thickness. And D is considered, depth of cut is considered as a width of cut, which is B. So F is equal to T and D is equal to B. Okay, so this will become area. This will become area. Feed into depth of cut. While solving the numerical, you have to consider that when F is given, that F you will consider as thickness of chip, and depth of cut is given in the numerical. At that time, that depth of cut you will consider as B, width of cut. Okay, so feed into depth of cut will become area. Why? Because in orthogonal cutting, that F is nothing but thickness of chip, that is T into B. Okay, so this will become area, and V is the cutting velocity meter per second. So metal removal rate will become here 1000 FDV mm cube per second. This is cutting velocity is given in meter. So for converting in mm, because this is in mm, this is in mm. So converting that mm per second, you have to multiply by 1000. So this will become 1000 FDV mm cube per second. Metal removal rate FDV. Okay, and U is the unit power defined as power required at cutting zone in watt to remove 1 mm³ of metal in 1 second. So power required for cutting will become here MRR into U in watt. Okay, MRR, this is nothing but 1000 FDV into U, that is nothing but U is specific energy or specific power consumption, where U is specific energy or specific power consumption. So specific energy is the energy consumed per unit volume of material removed. Specific energy is the energy consumed per unit volume of material removed. That means for removing 1 unit volume of material, mm³, how much energy is required? That energy is a specific energy, and that specific energy, if you multiply it to metal removal rate, this will become power. Okay, this will become power required for cutting. Metal removal rate into specific energy will become power here. So remember this formula. And the another formula for power in terms of force, if force is given and cutting velocity is given here, VC, that is actual VC, cutting velocity, and it is generally denoted by only V, and that V is nothing but cutting velocity. So power V is equal to FC into cutting velocity. If you multiply that and divide by 1000, you will get the power in kilowatt. Power is equal to FC into VC, cutting force into cutting velocity, divided by 1000, it will give the power in kilowatt. So at the end of the session, student, you can understood the empirical relation of stress, shear strain, energy and power that you have to write down in your notebook and remember in your mind also for solving the numericals. So thank you for watching this video.